Hello students, we are the main section. We are at the technical part of the statistics, that is the chi-square test. Objective: application of the chi-square test enables us to compare observed data with the data that we would expect to obtain according to a specific hypothesis. It can be employed when we wish to determine if a sample fits some theoretical distribution. Technically, it can be used to determine whether there is a significant difference between the expected frequencies and the observed ones in one or more categories. That is, do the number of individuals or objects that fall in each category differ significantly from the number one would expect? Is this difference between the expected and observed due to sampling error, or is it a real difference? Subject: an overview, bivariate tabular analysis, generalizing from samples to population, chi-square requirements, collapsing values, computing chi-square, interpreting the chi-square value, measures of association will be discussed. Chi-square is a non-parametric test of statistical significance for bivariate tabular analysis. Typically, the hypothesis tested with chi-square is whether or not two different samples are different enough in some characteristic. For example, if according to Mendel's laws, you expected 10 of 20 offspring from a cross to be male and the actual observed number was 8 males, then you might want to know about the goodness of fit between the observed and expected. The chi-square test is always testing what scientists call the null hypothesis, which states that there is no significant difference between the expected and observed result. A non-parametric test like chi-square is a rough estimate of confidence. It accepts weaker, less accurate data as input than parametric tests like t-test and analysis of variance. Chi-square is used most frequently to test the statistical significance of results reported in bivariate tables, and interpreting bivariate tables is integral to interpreting the results of a chi-square test. So, we will take a look at bivariate tabular analysis. Bivariate tabular analysis is used when one tries to summarize the intersections of independent and dependent variables and understand the relationship between those variables. For example, if you wanted to know if there is any relationship between the gender of Indian college students at a particular university and their footwear preferences, we might select 50 males and 50 females as randomly as possible and ask them, on average, do one prefer to wear sandals, sneakers, leather shoes, boots or something else? In this example, our independent variable is gender. In experimental research, the independent variable is actively manipulated by the researcher. For example, whether or not a rat gets a foot pellet when it pulls on a striped bar. In most sociological research, the independent variable is not actively manipulated in this way, but controlled by sampling. Example, males versus females. Bivariate tabular analysis is good for asking the following questions. Is there a relationship between any two variables in the data? How strong is the relationship in the data? What is the direction and shape of the relationship in the data? Is the relationship due to some intervening variables in the data? To see any patterns or systematic relationship between gender of undergraduates and college and reported footwear preferences, we could summarize our results in a table like this: male and female college student footwear preferences. In the column, we have sandals, sneakers, leather shoes, boots and others, whereas in the rows we have the gender, that is male and female. Depending upon how our 50 male and 50 female subjects responded, we could make a definitive claim about the footwear preferences of those 100 people. In constructing bivariate tables, typically values on the independent variable are arrayed on vertical axis, while values of the dependent variable are arrayed on the horizontal axis. This allows us to read across from hypothetically causal values on the independent variable to their effects or values on the dependent variable. For example, if values on an independent variable were arranged from lowest to highest value on the variable and values on the dependent variable were arranged left to right from lowest to highest, a positive relationship would show up as a rising left to right line. But remember, association does not equal causation. An observed relationship between two variables is not necessarily causal. So, one can see that crosstabs are structurally more suitable for analyzing relationship between nominal and ordinal variables. Interval and ratio variables will have to first be grouped before they can fit into bivariate table. Each cell reports essentially how many subjects or observations produced that combination of independent and dependent variable values. So, for example, the top left cell of the table answers the question, how many male graduates at University X prefer sandal? Answer, 6 out of the 50 sampled. Have a look at the table 1b, male and female college students' footwear preferences. Reporting and interpreting crosstabs is most easily done by converting raw frequencies into percentages of each cell within the values or categories of the independent variable. For example, in the footwear preferences, the table above, total each row, then divide each cell by its row total and multiply that fraction by 100. Percentages basically standardize cell frequencies as if there were 100 subjects or observations and in each category of the independent variable. This is useful for comparing across values on the independent variable, but that usefulness comes at the price of a generalization from the actual number of subjects or observations in that column in one's data to a hypothetical 100 subject or observations. The raw row total was 93, then percentages do little violence to the raw scores, but if the raw total is 9, then the generalization, that is on no statistical basis with no knowledge of the sample population representativeness, is drastic. So, one should provide the total n at the end of each row or independent variable category. With this civet in mind, one can compare the patterns of distribution of subjects or observations along the dependent variable between the values of the independent variable. Example, compare male and female undergraduate footwear preference. For some data, plotting the results on the line graph can also help one interpret the results, that is, whether there is a positive, negative or curvilinear relationship between the variables. Table 1c shows that within our sample, roughly twice as many females preferred sandals and boots as males, and within our sample, about 3 times as many men preferred sneakers as women and twice as many men preferred leather shoes. We might also infer from the other category that female students within our sample had a broader range of footwear preferences than did male students. Generalizing from samples to population. We usually want to measure a sample in order to know something about the larger populations from which our samples were drawn. On the basis of raw observed frequencies or percentages of a sample's behavior or characteristics, we can make claims about the sample itself. But we cannot generalize to make claims about the population from which we drew our sample, unless we submit our results to a test of statistical significance. A test of statistical significance tells us how confidently we can generalize to a larger population from a sample of that population. How does chi-square do this? Basically, the chi-square test of statistical significance is a series of mathematical formulas which compare the actual observed frequencies of some phenomenon with the frequencies we would expect if there were no relationship at all between the two variables in the larger population. In a sense, chi-square is a lot like percentages. It extrapolates a population characteristic, that is a parameter, from the sampling characteristic, that is a statistic, similarly to the way percentage standardizes a frequency to the total column n of 100. But chi-square works within the frequencies provided by the sample and does not inflate or minimize the column and row totals. Chi-square is a non-parametric test. It does not require the sample data to be more or less normally distributed as parametric tests like t-test do, although it relies on the assumption that the variable is normally distributed in the population from which the sample is drawn. But chi-square, while forgiving, does have some requirements. 1. The sample must be randomly drawn from the population. 2. Data must be reported in raw frequencies and not percentages. 3. Measured variables must be independent. 4. Values or categories on independent and dependent variables must be mutually exclusive and exhaustive. 5. Observed frequencies cannot be too small. As with any test of statistical significance, one's data must be from a random sample of the population to which one wished to generalize one's claims. Part of the chi-square mathematical procedure accomplishes the standardizing. So, computing the chi-square of percentages would amount to standardizing an already standardized measurement. Any observation must fall into only one category or value on each variable. For some variables, no other category may be needed, but often other ensures that the variable has been exhaustively categorized. In any case, one must include the results of the whole sample. Furthermore, one should use chi-square only when observations are independent. Chi-square is an approximate test of the probability of getting the frequencies one have actually observed the null hypothesis were true. It is based on the expectation that within any category, sample frequencies are normally distributed about the expected population value. Since frequencies cannot be negative, the distribution cannot be normal when expected population values are close to 0, since the sample frequencies cannot be much below the expected frequency, while they can be much above it. The smaller the expected frequencies, the less valid are the results of the chi-square test. Expected frequencies are derived from observed frequencies. Therefore, if one has cells in one's bivariate table which shows very low raw observed frequencies, that is 5 or below, one's expected frequencies may also be too low for the chi-square to be appropriately used. In addition, because some of the mathematical formulas used in the chi-square use division, no cell in one's table can have an observed raw frequency of 0. The following minimum frequency thresholds should be obeyed. For a 1 into 2 or 2 into 2 table, expected frequencies in each cell should be at least 5. For a 2 into 3 table, expected frequencies should be at least 2. For a 2 into 4 or 3 into 3 or larger table, if all expected frequencies but 1 are at least 5, and if the one small cell is at least 1, chi-square is still a good approximation. In general, the greater the degrees of freedom, that is, the more values or categories on the independent and dependent variables, the more lenient the minimum expected frequencies threshold. Collapsing values. A brief word about collapsing values or categories on a variable is necessary. First, although categories on a variable, especially a dependent variable, may be collapsed, they cannot be excluded from a chi-square analysis. That is, one cannot arbitrarily exclude some subset of one's data from one's analysis. Second, a decision to collapse categories should be carefully motivated with consideration for preserving the integrity of the data as it was originally collected. For example, how could one collapse the footwear preference categories in our example and still preserve the integrity of the original question or data? One cannot, since there is no way to know if combining, that is, boots and leather shoes versus sandals and sneakers is true to one's subject's typology of footwear. As a rule, one should perform a chi-square on the data in its uncollapsed form. If the chi-square value achieved is significant, then one may collapse categories to test subsequent refinements of one's original hypothesis. Computing chi-square. Let's walk through the process by which a chi-square value is computed. The first step is to determine a threshold of tolerance for error. That is, what odds are we willing to accept that we are wrong in generalizing from the results in a sample to population it represents. Are we willing to stake a claim on a 50% chance that we were wrong, a 10% chance, a 5% chance, 1% chance? The answer depends largely on our research question and the consequences of being wrong. If people's lives depend on our interpretation of our results, we might want to take only one chance in 1 lakh that we are wrong. But the stakes are smaller. For example, whether or not two texts use the same frequencies of some linguistic feature, we might accept a greater probability, it's 1 in 100 or even 1 in 20, that our data do not represent the population we are generalizing about. The important thing is to explicitly motivate one's threshold before one performs any test of statistical significance to minimize any temptation for post hoc compromise of scientific standards. For our purpose, we will set a probability error threshold of 1 in 20 or p at 5% level for our footwear study. The second step is to total all rows and columns. Look at the table 1D. The table shows male and female undergraduate footwear preferences, that is, observed frequencies with row and column total. The row and column total intersections are portrayed. Remember that chi-square operates by comparing the actual or observed. frequencies in each cell in the table to the frequencies we would expect if there were no relationship at all between the two variables in the populations from which the sample is drawn. In other words, chi-square compares what actually happened to what hypothetically would have happened if all other things were equal. If our actual results are sufficiently different from the predicted null hypothesis results, we can reject the null hypothesis and claim that a statistically significant relationship exists between our variables. Chi-square derives a representation of the null hypothesis, the all other things being equal scenario, the following way. The expected frequency in each cell is the product of that cell's row total multiplied by that cell's column total divided by the sum total of all observations. So, to derive the expected frequency of the males who prefer Sandel's cell, we multiply the top row total, that is 50, by the first column total, that is 19, and divide that product by the sum total 100, that is 50 into 19 divided by 100, that is 9.5. The logic of this is that we are deriving the expected frequency of each cell from the union of the total frequencies of the relevant values on each variable as a proportion of all observed frequencies. This calculation is performed to derive the expected frequency of each cell as shown in table 1E. We can informally analyze this table comparing observed and expected frequencies in each cell across values on the independent variable or across values on the dependent variable. Females prefer sandals and boots more than expected, but sneakers and shoes less than expected. But so far, the extra computation doesn't really add much more information than interpretation of the results in percentage form. We need some way to measure how different our observed results are from the null hypothesis. Or to put it another way, we need some way to determine whether we can reject the null hypothesis, and if we can, with what degree of confidence that we are not making a mistake in generalizing from a sample results to the larger population. Logically, we need to measure the size of the difference between the pair of observed and expected frequencies in each cell. More specifically, we calculate the difference between the observed and expected frequency in each cell, square the difference, and then divide that product by the difference itself. The formula can be expressed as chi-square is equal to observed minus expected the whole square divided by expected value. Squaring the difference ensures a positive number so that we end up with an absolute value of differences. For example, the difference between observed and expected frequencies for the male Sandel's preference is calculated as follows. Observed minus expected is the difference. The sum of all products of this calculation on each cell is the total chi-square value for the table. The computation of chi-square for each cell is listed below in table 1F. The total chi-square value for the table 1 is 14.026. Interpreting the chi-square value. We now need some criterion or yardstick against which to measure the table's chi-square value to tell us whether or not it is significant. What we need to know is the probability of getting a chi-square value of a minimum given size even if our variables are not related at all in the larger population. from which our sample was drawn. That is, we need to know how much larger than 0 our table's chi-square value must be before we can confidently reject the null hypothesis. The probability we seek depends in part on the degrees of freedom of the table from which our chi-square value is derived. Degrees of freedom. Mechanically, a table's degrees of freedom can be expressed by the following formula. Degrees of freedom, that is df, is equal to r minus 1 into c minus 1, that is row minus 1 into column minus 1. That is, a table's degrees of freedom equals the number of rows in a table minus 1 multiplied by the number of columns in the table minus 1. For 1 into 2 tables, degree of freedom is equal to k minus 1, where k is the number of values or categories on the variable. Degrees of freedom is an issue because of the way in which expected values in each cell are computed from the row and column totals of each cell. All but one of the expected values in a given row or column are free to vary. Once the free to vary expected cells are specified, the last one is fixed by virtue of the fact that the expected frequencies must add up to the observed row and column totals from which they are derived. Another way to conceive of a table's degrees of freedom is to think of one row and one column in the table as fixed, with the remaining cells free to vary. Consider the following visuals, where x is fixed. In a statistic book, the sampling distribution of chi-square, also known as critical values of chi-square, is typically listed in an appendix. One reads down the column representing a previously chosen probability of error threshold and across the row representing the degrees of freedom in a table. If chi-square value is larger than the critical value in that cell, data presents a statistically significant relationship between the variables in a table. Table 1's chi-square value of 14.026 with 4 degrees of freedom handily clears the related critical value of 9.49. So, we can reject the null hypothesis and affirm the claim that male and female undergraduates at college X differ in their footwear preferences. Statistical significance does not help one to interpret the nature or explanation of that relationship. That must be done by other means. But a statistically significant chi-square value does denote the degree of confidence one may hold that relationship between variables described in one's results is systematic in the larger population and not attributable to random error. Measures of association. While the issue of theoretical or practical importance of a statistically significant result cannot be quantified, the relative magnitude of a statistically significant relationship can be measured. Chi-square allows one to make decisions about whether there is a relationship between two or more variables. The null hypothesis is rejected, we conclude that there is a statistically significant relationship between the variables, but we frequently want to measure the strength of that relationship, an index of degree of correlation, a measure of the degree of association between the variables represented in our table. Luckily, several related measures of association can be derived from a table's chi-square value.